Hey guys, this is Darshan Lokhande. I am a pre-final year BTech CSE student at IIIT Pune. Welcome to our channel Learn Competitive Programming with CodeChef. If you are interested in competitive programming and want to learn data structures and algorithms, this is the one-stop destination for you. We post weekly problem explanations and concept videos. So don't forget to subscribe to our channel by hitting that subscribe button and also the bell icon. The problem that we are going to discuss today is fractions. The problem appeared in November lunchtime and has a difficulty level of easy medium. The prerequisites for this problem are Euclid's GCD algorithm and finding divisors of a number using the prime factorization. Our agenda for today's video is going to be as follows. First, we will walk through the problem statement and try to understand what the problem is trying to say. Then, we will walk through the detailed solution approach in which we will see the step-by-step approach to the solution. Followed by which we will be seeing the summary of the solution approach and then having a quick go through of the C++ implementation. The problem statement is pretty straightforward. It goes as follows. We are being told that for positive integers a and b, the fraction a upon b is said to be a good fraction if it is equal to m upon m plus 1 for some positive integer m. That is, for example, 2 upon 3, 4 upon 5, 7 upon 8 are all the examples of good fractions. Further, in the question, we are given an integer n and we have to find the pairs of integers I, j such that both I and j lie in the range 1, n, and also this expression, that is I upon I plus 1 into j plus 1 upon j, this fraction evaluates to be a good fraction. To understand this better, let's see an example. So in this example, the input, that is the number n, is given to be 5 and the output comes out to be 8. That is 8 pairs of the type I, j are such that the expression I upon I plus 1 into j plus 1 upon j evaluates to be a good fraction. So it is given here that the 8 pairs are as follows. So to demonstrate the evaluation, let's pick a random pair. So let's say for this pair, I is 2 and j is 4. So the expression would look like 2 upon 3 into 5 upon 4. So this evaluates to be 5 upon 6, which is indeed a good fraction. So this is a one pair. So similarly, if you calculate the answer for all the other mentioned pairs over here, they would evaluate to a good fraction. Not necessarily 5 by 6, but some other good fraction. So in this manner, we will be given an integer n as input and we just have to output the count. Remember, we don't have to output the actual pairs. We just have to output the count of how many pairs are possible such that they evaluate to a good fraction. Also, a side note that during the explanation of my solution, instead of I, j, I would be using the notation of a, b. So don't get confused with a, b. It is same as I, j. At this point of time, I would like to mention that if you haven't yet tried the question, give it a try and then come back to the video and continue with the editorial. To begin with our solution approach, observe that the constraints for subtask 1 are very small. That is, for subtask 1, it is given that n lies between 1 and 2000. That is, the number is very small, right? The upper bound on n is very small. So what we can do is that we can brute force over the pairs I, j. How? We'll just write two nested for loops. That is, one for loop is for I and I runs from 1 to n. Similarly, inside that there will be another for loop which runs for j and j also similarly runs from 1 to n. So in this way, all the pairs will be calculated. That is, for I is equals to 1, j can be 2, j can be 3 and so on. And similarly, if I is 2, then for I is equals to 2, j can be 1, 2, 4, 5 and so on, right? So we will brute force on all the I, j pairs and evaluate the expression, that is I upon I plus 1 into j plus 1 upon j. And once we have this fraction, we will reduce this fraction and we will check that whatever fraction that we are getting in the end, if the fraction is good, it would be of the form m upon m plus 1, and we'll just maintain a variable count which maintains that how many pairs are giving us good fractions. So using brute force we can easily solve the question for subtask 1, but that only gives us 5 points, right? So now let's proceed and see the math and the approach behind the 100-point solution. To start with, we know that a good fraction looks like m upon m plus 1, where m is some positive integer. So it is evident from this fraction that its value is always less than 1. Why? Because the denominator is greater than the numerator, right? So this is for the good fraction. So our target fraction, that is a upon a plus 1 into b plus 1 upon b, must also be less than 1, because we want this target fraction to be a good fraction, right? So if we do some rearranging in this target fraction, it will look like a upon a plus 1 is less than b upon b plus 1. And now we know that this inequality implies that a is less than b. So whatever pairs a comma b we would be counting, it is now evident that a is less than b in all of them. That is, the condition a less than b will hold true for all pairs a comma b for which this target fraction is a good fraction. Now we are only interested in finding the pairs a comma b such that the equation a upon a plus 1 into b plus 1 upon b is equals to c upon c plus 1 for some c. Okay, so if this LHS evaluates to c upon c plus 1, it means that it is a good fraction, right? So this is what we are aiming for. So now in this equation, if we try to do some rearranging and try to find c in terms of a and b, then on the LHS we have ab plus a upon ab plus b is equals to c upon c plus 1. Then if we do cross multiplication, we have c into ab plus a plus ab plus a is equals to c into ab plus b. And now we can take c on one side and simplify this as c is equals to ab plus a upon b minus a. So this right here is the equation of c in terms of a and b. But wait, we just now saw that for all the possible pairs a comma b, the condition a less than b always holds true. It means that we can write b as a plus d, where d is some positive integer, right? Because a and b are also integers, so we can definitely write b as a plus d. So if we substitute this thing into this equation, the new equation would look like c is equals to a into a plus d plus 1 divided by d. So this right here is the new equation of c in terms of a and d. So what we have done is initially we took our target equation, rearranged it to find c in terms of a and b, and then substituted b as a plus d to get this new equation. So now that we have this fraction, there can be some common factors between the numerator and the denominator, right? So for example, if we take this term a upon d over here, the maximum common factor that we can get by a upon d is nothing but GCD of a comma d. Similarly, if we decide to take a plus d plus 1 with d, then the maximum common factor that we can get is GCD of a plus d plus 1 comma d, right? But now observe that from Euclid's GCD algorithm, we know one more thing. We know that GCD of a comma b is nothing but GCD of A minus B comma B. So this equality holds. So if we apply this thing on this expression, we can reduce this to GCD of A plus 1 comma D. So what are the maximum common factors that we can get? One is GCD of A comma D and the another one is GCD of A plus 1 comma D. So now we have to focus that C has to be an integer, right? So for C to be an integer, the denominator D has to cancel out with some divisors of the numerator, right? Only then the C would be an integer, right? So what we can do is that we can set the value of D as x dash into y dash, where x dash is some divisor of A and y dash is some divisor of A plus 1. Because just now we saw that from this term A upon D, we can get GCD of A comma D as the maximum common factor, and from the other term we can get GCD of A plus 1 comma D as the maximum factor. So we are setting D as x dash into y dash, where x is some divisor of A and y dash is some divisor of A plus 1. That way it cancels out with the divisors of the numerator. And note that A and A plus 1 are co-prime with each other, meaning that they don't have any common divisors. So it is guaranteed that the values of D that we would be getting, that is x dash into y dash, would be unique. But still, how do we count our final answer? So for that, we know that we have to find the pairs A comma B, right? And we know that A is always less than B. So what we do is we try to find the answer for all the possible values of A. So A can take the value 1, 2, 3, all the way up to n minus 1, right? So what we do is that each time we find the divisors of A. So we find a list of all divisors of A, and similarly we also find the divisors of A plus 1. So now we have the list of divisors of A and A plus 1. Let's say there are m elements in this list and n elements in this list. So we cannot say that as D has to be of the form x dash into y dash, where x dash belongs to this list and y dash belongs to this list, the total number of ways of D will be m into n. No, we cannot say that directly. Why? Because there is one more important condition that we have to apply. That is, the numbers a and b itself should lie in the range 1, n, and that we are forgetting. So A already lies in the range 1, n, as we can see, and we also know that B is written as A plus D, and if we substitute the value of D, then it is A plus x dash y dash, right? So B is equals to A plus x dash y dash, and now we have to apply the inequality that A plus x dash y dash should be less than or equal to n. Only those value of x dash and y dash are acceptable, not all the combinations of x dash y dash. Only those combinations are acceptable for which a plus x dash y dash is less than or equal to n, so that a and b lies in the range 1, n. So how do we do that? Let's see. So to find the pairs of x dash y dash for which this whole inequality holds true, there are several methods, such as the two-pointer method or the binary search method. So I will be discussing the two-pointer method over here. So what we can do is that we can list out all the divisors of A in a sorted manner. So these are the divisors of A in the sorted manner, and similarly the divisors of A plus 1 are also listed in a sorted manner. And what we can do is that we can place two pointers, one at the beginning of divisors of A, let's call this pointer L, and one more pointer at the very last of the divisors of A plus 1. Let's call this pointer as R. So what we do is that temporarily we fix this pointer over here and check if the value present over here and the value present over here satisfy this condition or not. If they do not satisfy the condition, we move the pointer of R towards left and we keep on doing until this condition is satisfied. And once the condition is satisfied, we increment our answer by R. And that's it. That's our process. What we do is that for each position of L, we keep moving R towards the left until this condition is satisfied. And once the condition is satisfied, we increment our answer by R. And we do this for all the positions of L. And that completes our process. And this sums up our solution along with a bit of implementation or the idea of the two-pointer approach. Now, to summarize our solution approach, what we are going to do is that first we would be taking the input of n, then we run a loop which goes from I is equals to 1 to n minus 1, and these are nothing but the values for a. And each time what we will do is that we find the divisors of a, we also find the divisors of a plus 1, and we count from these two sorted lists that what are the possible pairs of x dash comma y dash such that a and b are in the range of 1 and n, and we do this for all the values of a from 1 to n minus 1. And how do we find this count? We just now saw that we would be using the two-pointer approach as these lists are sorted. So we would be using the two-pointer approach to find the count of the x dash comma y dash pairs for d, which result in a and b being in the range of 1 comma n. Also, did you know that CodeChef also conducts free live classes on Unacademy where we teach every possible topic on competitive programming? We have beginner level courses like Introduction to Programming in C++ or Java, basic data structures, recursion, as well as advanced courses like dynamic programming, graph theory, and segmentaries. These courses are conducted by top coding experts who have been ICPC World Finalists, IOI medalists, or have worked in top product companies like Facebook, Google, Amazon, LinkedIn. All you need to do is download the Unacademy app or register yourself at unacademy.com and select your goal as competitive programming. You can also take the paid plus subscription to get additional features and individual level support. In plus subscription, we have a large set of problems associated with each topic covered. Not only that, we also have 6-star and 7-star rated teaching assistants to clear all your doubts during and after the live sessions. Also, don't forget to use my referral code DarshanCool25 while subscribing to get an instant 10% discount. So now we move towards the implementation of the code. So as you can see here that I start my code with initializing my sieve because I would be needing the prime numbers and the prime factorization to find the divisors of a number. So I initialize my sieve. You can see over here that it is a function which calculates the prime numbers and the smallest prime factors for each of the numbers. So think of this sieve function and this divisors function as a helper function which directly gives me the divisors of a particular number. So if you consider them as a black box, continuing with our code, we take the input of n and initialize an answer variable to 0. Then I have set current and next as two vectors containing the divisors of the numbers 1 and 2 respectively. So initially my a would be 1. So the factors of 1 or the divisors of 1 are simply the number 1 and divisors of 2 are 1 comma 2. So I store the divisors in these vectors known as current and next, and just ignore these 3 lines for now and focus on these 4 lines. So what I do now is that I set my R pointer at the last position of my next vector. Okay, so these are the divisors of my a plus 1 number. So I set my R to be at the last position over here, and I set L, which goes from 0 to the current dot size, that is the size of divisors of A. And for each of these L, what I check is that if the condition for B is violated, I move my R pointer one position towards the left, and I keep on doing this until this condition is true, right? And once this condition is false, it means that now my both the numbers a and b are in the range 1 comma n, so I increment my answer by r. That is, for that particular value of L, there are r possibilities of y dash for which my answer lies in a good range. And I do this for all the values of a, that is from 1 to n minus 1. And these three lines which we had skipped, they are nothing but initially the value of a is 1 and the value of a plus 1 is 2, but in the next iteration the value of a would be 2 and the value of a plus 1 would be 3. So I don't again count the divisors of 2. I already have the divisors of 2 in next. So what I do is that I simply swap current and next, and I find the divisors of I plus 1 and store them in the next vector. And you can see these helper functions help me to find the divisors. They basically use the pre-computed smallest prime factor of each number and the property of prime numbers, using which I can find all the divisors. And the most important thing, don't forget to do it, is that after finding the divisors, don't forget to sort them, because only then our two pointer approach is going to work. It is whole and sole dependent on the sorted property of the divisors present in the list. That is why the pointers L and R are functioning, and it is happening in a efficient manner. And that's it. That completes our solution. Once we have calculated the answer for all the possible values of A, we just output the answer. So without wasting any more time, let's submit the code on CodeChef ID and let's hope for a quick AC. Great, so our solution works.